Stanford University.
Hello, everybody, and welcome. Stanford CS 193P Spring of 2020. This is Lecture 3. I'm going to start today with a demo. We're going to demo that reactive SwiftUI stuff we were talking about. Then I am going to jump into some slides, talk a little bit more about the Swift type system, specifically protocols, and then kind of a totally different topic after that, which is the layout system for views, how they get laid out on screen. Time permits, I'll actually do a little demo of that layout stuff at the end of today. If not, that'll be pushed to next time. And next time, we're definitely going to lay out our cards in rows and columns instead of all in a horizontal line like they are now. And we'll also get started on actually having our model play the game and implementing some of our logic. But for now, let's do this reactive Swift demo. You're all really familiar now, hopefully, with MVVM. But before I start with this demo, I'm going to take just a quick second to review it, just in case maybe it's been a few days since you did your homework. Here is our model. It's called Memory Game. It has this don't care card content, which is what's on the card, which as a model, we don't care. That's up to the UI to decide what it wants to show on the cards. Here are our cards. It's an array of this card struct right down here. And this choose lets us essentially play the game. We haven't implemented any of that yet, but when you choose a card, that's when the matching happens and things like that. And here's how we initialize or create our memory game. We obviously want to specify how many pairs of cards in our game, and we need a card content factory function here to make the content that's on the card, because for us, it's a don't care. So somebody who does care has to make that for us. And here's our view model. Our view model has a var, which is the model. Our view model can talk to the model all at once. It's a portal or doorway onto the model for the view, so it has to be able to do that. Notice that there are no vars in here to point to the view. The view model never talks to its view. It's the view that talks to the view model. And we're going to see how the view and the view model kind of interact in just a moment here, but there's never going to be any connectivity from the view model to the views, because many different views will be using this view model, this portal, this doorway onto the model. They'll be using it, sharing it. Again, that's why our view model is a class. It's a pointer into something in the heap. It's easy to share something that's pointed to. So our view model also provides public access to the model, which is otherwise private. And that access is both getting information, like getting the cards, and also letting the view express its intent, in this case, to choose a card. Both very easily implemented by us with our model, but this is what our view model's job is. And finally, we have our view. We have two views in our view in the MVVM view sense. One is a view that represents a single card, and then this view, which is all of our cards combined here. And based on the feedback that I got from some of you working on your homework assignments this week, I want to clarify a little bit our thinking by clarifying the words we use to describe things. A number of you were saying things like, oh, I'm using this function to set the font of my card. And while I guess that's not exactly not right, it's really a better way of saying it is that this function right here modifies the view we send it to so that it uses this font to draw. And what's the difference there? Well, it's the difference between declarative programming and imperative programming. In declarative, we're just declaring that this is the font that is used to draw this view. Whereas in imperative, you're thinking things like, oh, I'm calling this function to set the font. Like at a certain moment in time, I'm setting it. And there's no moment in time with this declarative. At any moment in time, this should draw the view that reflects the model. And it should be able to do that anytime this body is requested. Boom, it should be a view that reflects the state of the model. essentially time insensitive. One other thing about this body is that this var, you never access this var. The word body is never going to appear in your code. This body is called by the system. Every time the system wants to draw a view of the model that this represents, it will call this var to get that view. So this is called by the system. Your job is to implement it by declaring what the view is, given the current state of the model that you see through this portal, the view model. And the last thing I want to talk about is some people were inside these view builders, like in for each or even inside ZStack or HStack. Remember, these are view builders, and view builders are cool because they're functions that return a view, and they do allow this limited if-then, and they allow you to just list views. Instead of having to put them in an array or something, you can list them. People were wanting to put a var here, var x equals something down here. And of course, you cannot create vars inside the view builder. Okay, vars cannot be created inside these view builders. Just not allowed to create vars. So how do you do it? There's two ways to do it. One, you can put vars outside the view builders, just in your normal function, and then I could use x inside here. But of course, if I do that, now I've created this two line, I'll have to say return ZStack, but that's okay, I could do that. Another way, and probably a more common way, is to create another, let's say this wants to be an int, computed property, and just return whatever the value you want x to be. And now you can use x in here, and it's just going to use this computed property to calculate the value of x that it wants. So that's the way we deal with essentially creating local variables or variables that we need to do our drawing in here. And this is currently called content view, by the way, because that's where we started with that template from Xcode. Xcode didn't know we were doing a memory game at the time, so it called it content view. Thought before we started, I would show you how we could rename that to be a much better name. Now, you might be tempted to do this in the navigator with the search and replace feature here. And you can do that by going here to replace, and then you could search, for example, for content view. It would find all the places it's referenced, and then you could replace it with something like emoji, memory, game, view, or something like that. But actually, this is not how we would do this. If we're going to change the name of a var or of a type, we are going to use refactoring. Okay, so the way we do that is we're going to hold down the command key, command, and click. And when we command click, we get this nice menu here. We can jump to the definition of a type or a var or something. Or we can also rename. Okay, so we do that command click, and we're going to go rename. And it's showing us here all the places that it found content view, essentially the same thing as we did the search over here. Some of them it's going to change, and you can tell with this little check mark the things it's going to change. So it's going to change this file name, so it's going to change the name of that. That's good. Here it's showing the content view, but it's not going to change that. You see, it's not blue, it's gray. It's just saying I found this, but I'm not going to change that because I'm not sure that that's really referring to this type since it's in a comment. So we'll have to change that ourselves. It's going to change down here. This var previews, that was actually that code we scrolled out of the way at the very beginning that shows our content view in the gray preview window over here. So that obviously would need to be changed. And then here's the code in the scene delegate where we're actually creating our memory game and then passing it into this top level content view. So when you do this command click and rename, it actually selects what you command clicked on, and you can just type something new. So emoji, memory, game, view, and see it's changing it in all the other places, not here though. And that's it. So you just hit this rename right here, and it has renamed it. Even the name of the file over here was nicely renamed. And we can go back and fix the things that it wasn't sure about, things like comments right here. Say this is our emoji, memory, game, view.swift, which in fact is the name of this file. So that was just a little aside. So for renaming, because sometimes you'll pick a name for a type or a var, and then you'll decide, I don't really like that name. It's not, because naming is really, really, really important. Can't overemphasize how important it is to pick good names for things. So being able to rename after you change your mind, really, really important. Our topic today, though, is going to be this reactive. I told you that SwiftUI is reactive. What do I mean by reactive? I mean that when changes happen in the model, they automatically are going to show up in the view. And currently, our UI is not reactive. So that's a problem. And let's take a look and see how we can fix that problem and make it so it is reactive. We're not going to, implement our entire memory game here with all the card matching. We're just going to take a baby step forward, which is we're going to make the cards flip over. That's part of our model. Essentially, the first step of our game logic is to have a card, when we choose it, flip over. So I've moved over here to my model code, where currently we just say card chosen when you touch on a card. Remember that from last time. Now I want to start actually implementing my game logic, starting with flipping the card over. Now you'll look at this and you'll think, oh, this is easy. Card.isFaceUp equals not card.isFaceUp. Right? Somebody is passing us the card they want to choose as an argument, and I'm just going to have the isFaceUpness of it be toggled or flipped to its opposite here. And this has an error, which is it cannot assign to property card is a let constant, which it is. All arguments to functions are essentially let. You don't type that let, but they are a let, so that's one problem, but it's actually much, much worse than that. It's not just that this is a let. This is a card. A card is a struct. Structs are value types, as we talked about last time. And a value type, remember, is copied every time it's passed as a parameter to a function or even assigned to another variable. Copy, copy, copy. It's always being copied. So this card here is a copy of one of the cards here. The view model got it or handed it out to a view, and when the view got it, it was a copy, maybe even a copy of a copy. So this is not actually a card that's in the array, it's a copy of that. Every time we pass a value type, it gets copied. So even if we could do this, which we can't because of that problem where this is essentially a let, it wouldn't be doing the right thing anyway. This would just be changing this guy to its face up to be swapped. It's having no effect on this one right here. So let's try something totally different here. Let's try and find out the index of which card in this array that this card is. I'm going to do that by saying let chosen index, which is going to be of type int. I'm going to equal to, I'm going to call a function on myself, index of that card. So index of, I'm going to write a function, it's going to be a function in myself of this card. So I'm going to find this card, find out what index it is in this array. So if you have func index of, which is going to be of type card, it's going to return an int, and this int is going to be the index into this array. Now, maybe I would say let chosen card, which is going to be of type card, equal my cards at that chosen index. Sounds good. Now I can say, now let's flip the card over. Its face up equals not chosen card dot is face up. Okay, so this seems like this is a good idea. We'll have to implement this in a minute, but this seems like this would be great, right? Now we are getting a card out of the array and we're flipping it over. But this too is not going to work for exactly the same reason. When we make an assignment to a var, okay, this chosen card, this equals copies this out of here. It copies the card out of the array. So even just making an assignment to another variable copies a value type. So now you're probably like, well, how are we going to change this thing? Well, we have to change it in place. Instead of changing a copy of this thing here, we're going to change this array itself, this array of cards. We're going to reach in there and change whichever is the right card to be the different face up. So we're going to do that. Still going to do self.cards chosen index, but instead of this indirection through a var that would copy it, I'm just going to have that thing directly is face up equal not that thing directly is face up. So I'm just going to flip the card over directly inside the array. A couple of things going on here. One, notice I'm putting self dot in front of every access to my variables and to functions I'm calling on myself. This self dot is optional in the vast majority of cases. And normally I would even say, don't put it there. It's just extra cruft. However, because of this thing I talked about last time where they're going to make it so even in the few cases where you do need a self dot, like here, self dot is actually required in our view. When we did our tap gesture, this self dot, if you take this away, it's going to have an error. You have to do the fix it to fix it. Remember that? So they're going to take this away. And when they take that away, then you're going to need self dot almost nowhere. So at that point, I don't know if that's 2 months from now. It's not clear. You know, WWDC is at the beginning of June. A lot of times they'll come out with new software, beta software at least at that point. Maybe they'll fix it then. I don't know. I don't work at Apple. I don't know anything what their plans are. But we do know that it's been publicly approved to get rid of this self dot. So in this course, just for the next 7 or 8 weeks or left in this course, I kind of recommend maybe just putting self dot in front of everything because it doesn't hurt anything and it'll keep you from running into this problem where you have to do the fix it. You're just learning this stuff and that's going to kind of give you the muscle memory of always typing self dot, which you'll have to train yourself out of in a couple months when this public fix comes out, but it'll keep you out of trouble in this quarter. So that's my recommendation, but in your homework, we're not going to say, oh, that's wrong, you put self dot, or oh, that's wrong, you didn't put self dot. It's totally up to you. I'm just trying to head off possible problems for you. So go for self dot is probably my recommendation. Okay, but we put this in here and we were sure this was going to work. We're for sure changing is face up in that array. There is no doubt self.cards of chosen index. We are changing this array to have its is face up be toggled, and yet we still have an error here. Cannot assign to property self is immutable. It's not saying that this cards is immutable because the cards is not. It's a var. If it were a let, it would be immutable, but it's a var, so it's mutable. But it's self itself that is immutable. In other words, our own function doesn't seem to be able to modify our self. How do we do anything then if we can't do that? Well, what's going on here is that I told you these value types, Swift is not doing a bitwise copy. It's not actually copying them from one place in memory to another when you pass them around. That's the semantic. That's how you have to imagine it's happening. But it's really only actually making those copies in memory when you start changing something, which we are doing here. Okay, we are changing this array, and this is our actual property, so we're not making a copy, it's actually changing the array. But this method changes our self. It modifies our self because it changes our cards. So we have to let Swift know that by saying that this is a mutating function. So all functions that modify self have to be marked mutating in a struct. This is not true in a class. Classes are in the heap. We have pointers to them. We can always change things that are in the heap, always modify things through a pointer, which, as I talked about before, can be a bad thing just as much as a good thing. But for structs, no, because they're value types, we have to let Swift know we're changing this. Now, index of, which we're going to write in a second here, it's just getting the index of a card in this array. It's not actually changing anything. It's just getting the index. So it does not need or want mutating here. And similarly, or inversely, our initializer is implicitly changing ourselves. We're creating ourselves. We're setting all of our variables here. So of course this is mutating. So you don't say mutating init. All inits are mutating. It's all part of the cool feature of value types that Swift knows when they're changing. And you're going to see that that has other benefits other than just this copy on write behavior as we copy things around. Index of card. How are we going to find out where this card, okay, that we're getting the index of is in this array? We want the index into this array that has this card. This turns out to be super easy for us because card is identifiable. Since it's identifiable, we can just look at its ID and uniquely see which card it is. So we just need to do a little for loop here for index in 0 ... less than our cards count, or again, if we're doing self.cards.count, either way, it's perfectly fine. I'm just going to go through every one, and I'm going to say if self.cards at that index ID equals this thing right here, okay, 2 equals, by the way, of, I guess, .id, then I can return this index because I found it. Here I'm looking at my array to see if the index, if the card at that index, its ID is the same as this one you passed. Now, you can already see a problem here. Of, really? Of. We're going to call this variable of. No, we don't want to call this of. Of is just something that makes it nice for people who call us to say self index of card. That's why we have this dual labeling of external name, internal name. And that allows us to call this card.id, but callers still get to say index of card. This is a great example. Hopefully you totally see why we have external names and internal names of arguments. We didn't do it here, okay? The external name and the internal name are the same. There's kind of an argument here. You might actually put the underbar here on choose because it's clear that we're choosing a card. That's the type of this argument. What else would we choose anyway? But I'm going to leave it this way just so we don't have to change our other code. But if you read the guidelines as part of your homework last week, you'll see that this is one where maybe an underbar would be there, and then people would just say choose and provide the card as the argument. There would be no label for the callers. We've done our for loop. We've found this. Well, it's still complaining here. Missing return in a function expected return int. Oh yeah, what if this for loop goes all the way through and never finds that card? Then we've got to return something here. So Swift actually has a fantastic thing to return here when this happens. Like you go to find something, you can't find it. In other languages, you'd probably return -1 or some bogus thing here. I guess I'll return, maybe you'd return 0, which is the first element, which is totally wrong, right? If you go look for the card and you can't find it, you're going to say, well, I'll return the first card, even though you know that's not the card. So it doesn't really matter what we return here for now because this is all just wrong. But I am going to put a little thing called a to-do here. It's a bogus. And a to-do is something you can go back later, / to-do, and find, remind yourself you need to fix this. And these show up here along the top where it says index of. If you click, right, this is a list of all my vars and funcs. Look, bogus appears right there. And if I click on it, it takes me right to bogus. And we will come back when I show you this cool way that you can return things like I couldn't find it from Swift. We're going to cover that probably next lecture. Then we'll fix this. We'll fix this. But for now, we're going to do this bogus thing right here. So we have index of card. We are definitely flipping the card over here. So let's run and see if this is working. Because we know we already have this hooked up to choose a card there. So now it should choose, say, card chosen, and also flip it over. There we go. Ready? Ghost. Oh. Pumpkin. Huh. Well, it's definitely accessing the model here because we're getting this card chosen. But how come these cards are staying face up? What is going on here? Well, what's going on here is we haven't implemented the reactive thing. I told you at the start of this, that's why we're here today, is to do this reactive thing. And you can see why we need the reactive. We chose a card it went here and changed the model. It flipped a card over, and yet we didn't see anything in the UI. And never should that be the case in SwiftUI, ever. When you change the model, the UI should update. How do we make that happen? If you remember from my MVVM slides, I put some keywords on the screen there, and I said, oh, these Swift keywords, we're going to use those to do this reactive, and that's exactly what we're going to do right now. And we're going to start in our view model. So here's our view model, and the way we make the view model participate in this reactive thing is using a constraints and gains thing called observable object. Now, remember constraints and gains, also known as protocols, by the way. These constraints and gains, we used one over here, :view. That was a constraints and gains. We were kind of constrained that we had to implement this body, but we gained all these other functions that we can send to view. So this one was a huge gains for a very small constraints, okay, to do view here. We also did it in our model. Our card, we did constraints and gains to be identifiable, which required us to do this var id int, but now we gained the ability to tell which card is which. And the UI is going to use that right here in this for each to make sure that if our cards move around or whatever, we can track where they are and animate them. You're going to see animation in SwiftUI is ridiculously easy, and a lot of it is because of this mechanism. So this constraints and gains right here, the constraints are almost none. You don't have to implement any vars or funcs, no body or ID or anything like that. The tiny little constraint is that it only works for classes, observable object. You can only be an observable object here if you're a class. So that's a minor constraints there. Now, the gain you get by doing this is you get this var called object will change. This var right here, you don't have to put it here like we did with body. You get it for free behind the scenes. So this will not be here. I'm just showing it to you what you're getting. And this var is not really of this type, observable object publisher. It's a little more complicated than that. We don't even know or care what it is really, but there's two things about this var that we need to know. One is that it's a publisher. Okay, meaning that it can publish to the world, to anyone who's interested, and our views are going to be interested when something changes. And there's only, this var can only be sent one function, which is the function send. And if you call the function send on object will change, it's going to publish to the world something changed about this object, or really something will change very soon. And so get ready and then react to it. And that's it. That's all we have to do really to have our view model participate in this. So every time our model changes, we want to do object will change dot send. For example, here's an intent. Clearly we're changing our model right here. We know that choose card is a mutating function right here. So of course that's going to change our model. So here we would just say object will change dot send. This is the only function really we're ever going to call on this object will change thing right here. And this is going to publish to the world object will change, meaning this memory game will change. That's all. It's not saying how it changed, it's just it changed. And that's important to know, because if this view model changed, this portal on the model has changed, views that are looking to that portal need to redraw themselves. And we're going to show you in just a second how they sign up to do that. So again, we don't need to put this in here. We get it for free. When I get rid of that, you can see no errors. This is all perfectly legal. You can call this anytime you want, anytime something changes. Doesn't even have to be your model changing. You could, if you were going to change these emojis, for example, you could call object will change. Totally up to you. However, in a significant app, you're going to have possibly a lot of intents, a lot of different things that might change your model. And it's a little bit annoying to have to say object will change.send, object will.change. It's even error prone. What if I, oopsie daisy, forgot to put this in there? okay? And then you choose a card and it's like, ah, the cards still don't flip over. Why? Because I forgot to put that in there. So while we can call object will change.send anytime we want, usually the way we deal with this is we take this var and we make it published. So this is not a Swift keyword. You can see it's not magenta. It's something called a property wrapper. This is a property. And property wrappers add a little functionality around a property. In this case, what this wrapper does is every time this property, this model, changes, it calls object will change.send. That's what it does. So really, to make it so that our observable object here, our view model, broadcasts every time something changes, we just need to @published all of our vars that we care whether they change. In this case, it's just our one model var. It could be other things as well. Okay, you can have as many of these @published vars as you want. Anytime any of them change, it's going to object will change.send. That's what it does. Okay, this looks a lot nicer than having to remember to put object will change.send in all these functions. You still have the option of doing object will change.send even if you use these, but most of the time you will not have to do object will change.send. All right, so we're almost there. Right now we've got our view model, so it's publishing every time the model changes. Now we just need to fix our view over here so that when it sees this view model publishing, it redraws. Okay, redraws every time it sees this thing say object will change.send. And the way it does that is with another property wrapper on this one called @observed object. And that's saying this var has an observable object in it, which it does. Emoji memory game is an observable object. And every time it says object will change.send, redraw. And of course, redrawing this one is going to cause this one potentially to get redrawn as well. Now, you might kind of feel like, whoa, this could be really inefficient. What if the model is changing all the time? Are we going to be redrawing our views every single time? Well, yes and no. Yes, we're going to be reacting to object will change and redrawing, but SwiftUI is smart about seeing whether something actually changed. So if we flip one card over, it's not going to redraw every single card, just the one that changed, and it knows because the cards are identifiable. You're starting to see why this for each on this array of cards forced us to make this identifiable. It helps it to understand, oh, this one changed, so I actually need to redraw that. Because actually calling this code is probably not very expensive. Actually drawing on screen, that's pretty expensive. So SwiftUI does everything it can to avoid doing that. But conceptually for us, it's so simple. Every time our model changes, this @published wrapper notices that we're an observable object, so our view can mark that it's interested in that publishing, and voila, it's going to redraw this. And this is how we do reactive programming. It's really, that's all there is to it. We're going to see some minor refinements to that down the road, but this is essentially how it works. So let's see if it works. Let's go run our app. Hopefully, when we click on the cards, we're going to say card chosen, but they're also going to flip over. So let's try the ghost. Woo! The ghost. I'm clicking on it. It's flipping both ways. How about this guy, this guy, and this guy? All right. So what's happening here is we are clicking on these, doing this on tap gesture. It's expressing this intent in the view model. The view model is then asking the model to go ahead and do it. The model is doing this mutating thing. Once it's done this mutating thing, it's easy for this to notice that this has changed, and it gets published, object will change.send, and this guy observes those object will change.send and is redrawing. That is the slides that I showed you, the back and forth. That's what it looks like in code. All right, so we need to jump back into the slides right now and talk a little bit about protocols. A protocol is going to look to you like it's a stripped down class or struct. Stripped down because it has functions and bars, but no implementation. So here's a protocol. movable that I've made up. It has one function and two vars. One of the vars is read only there, has moved. You can see it has that curly brace get there. And then distance from start is actually readable and writable. So that's why it has get and set. But there's no implementation here. Even those curly braces there, that's just saying whether those vars are read only or not. That's all there is. Once you have a protocol declared, now any type, struct or class, can come along and say, yes, I'm going to implement that. Okay, that's claiming to implement the protocol. So here I have the struct portable thing, and it says :movable in its declaration. And when it says that, that immediately means I sign up to implement this, and therefore it must implement every var and every function in movable. Now we've seen this before, view. We have our content view, :view. It signs up to be a view, and that's why it has to do var body. Same thing, card was identifiable. It signed up to implement identifiable. It had to implement that var ID. Now, it's also possible to have one protocol say that it requires another protocol. This is called protocol inheritance. Don't get confused with class inheritance because we're just talking about protocols here. So here I have a protocol vehicle, and it's inheriting from movable. It adds its own var there, passenger count. So if a class like car comes along at the bottom here and it says, oh, I sign up to be a vehicle, well, now it has to implement all three things from movable, and it has to implement the thing from vehicle. You can also, if you're a struct or a class, claim to implement multiple protocols. So here I have the class car. It's not only saying that it's a vehicle, but it also that it's impoundable and leasable. And now cars can have to implement all the functions and vars in all three of these protocols. Now a protocol is a type. That means that most protocols can be used in most circumstances where you have a type. For example, I can have a variable m of type movable. That's the type of m. It's of type movable. And what does that mean? Well, if I had another couple of vars like car and portable, which are of type car and type portable thing, then I can say m equals car or m equals portable. Why can I say that? Because car is a movable. It implements the movable protocol. In fact, car implements vehicle, vehicle inherits movable, and so therefore car is a movable. And this is great because now I have this variable m. I can start sending it functions like has moved, asked it has moved, because I know that m is a movable. And whether it's a car in there or a portable thing, we know that those vars and functions are going to be implemented because you're required to implement them if you say you're one of those things. But one thing to be a little careful of here, you cannot say portable equals car. The var portable up there is not of type movable. It's of type portable thing. Different. And so a car is not a portable thing. They're both movables, but a car is a different type than a portable thing. I think a car was a class, portable thing was a struct, so it's not even the same kind of thing. So you cannot say that. While I can say that m equals each of those things, I can't say they equal each other because Swift is enforcing the type of the var. And then when I say portable equals, the type of the var is portable thing, not type movable there. One way to think about protocols, and I've already mentioned this in the demo, is constraints and gains. I use this because it rhymes, so hopefully easy to remember. And it works like this. So I have this struct right here, Tesla, and it's a vehicle, so it implements all those things. In fact, it's constrained to implement all the things in vehicle, which includes all the things in movable. But that being constrained on that is going to make it gain all the things that world offers to a vehicle. Now you might be saying, well, wait a second here. Vehicle is a protocol, has no implementation. How are we possibly going to gain anything here? All right. It just seems like I got all constraints here and I got no gains. Well, the magic is in the keyword extension. In Swift, we can extend protocols to have implementation. And we just say extension, name of the protocol, and then we can put functions with implementation, functions and vars with implementation. Now, we can't have any vars that have storage here. So there is that restriction. It has to be computed vars, like var body was computed. Remember, it had the curly brace. Have to have the same thing here. But we can add as many things as we want. With this extension of vehicle, register with DMV, now Teslas and all other vehicles can be registered with DMV. In other words, they gained that ability by living with the constraint that they had to implement those methods and vars that were in those protocols. So yeah, this is really the center of functional programming in Swift, and the protocol Vue is probably the poster child for doing this, and we're going to see more about Vue in a couple slides here. In addition to adding functions like register with the DMV, you can also use an extension to protocol if you want to add default implementations. So here I'm extending movable, and I'm actually providing a default implementation for has moved. As has moved is one of the vars in the protocol, but I'm providing a default implementation here. I'm just looking at my distance from start, and if that's greater than 0, I'm going to assume I've moved. Okay, and I'm doing this with an extension to movable. So this makes it possible for me then to have a struct. I have one here called chess piece, which is a movable. You can move chess pieces. Chess piece does not need to implement has moved. If chess piece just implements move by and distance from start, then it will have successfully implemented movable because it'll pick up the default implementation from that extension right there. Now, if chess piece wanted to implement has moved itself, it could, but it doesn't have to because there's a default implementation for has moved in that extension. Now, you can use extensions, of course, to add code to structs and classes as well, not just protocols. So here, for example, I have a struct called boat, and it's got its own methods, whatever they might be. And here I'm adding extension to boat, a function sail around the world. And this extension, you can see, has curly braces. It has an implementation. This is an actual implementation of sail around the world that we've added to boat. You can even make something like a boat conform to a protocol purely by using an extension. So boat doesn't implement any protocols right now, but I can make boat implement movable by having an extension to boat that says :movable, and then in that extension, implement move by and distance from start. Now boat is a movable, and I added it totally with extension. It's not an uncommon thing to do, to take a struct or a class and make it conform to a protocol using purely an extension where you add the code in an extension. Why do we do all this protocol stuff? Now, for those of you who are coming from object-oriented programming, this is going to seem like, what's going on here? Why do we do this? Well, there's a really good conceptual reason why we're doing this. Protocols are a way for types, structs and classes, other protocols, even enums, which we haven't talked about, to say what they are capable of, what functions they can do, what vars they have on them. And it's also a way for other code to demand certain behavior from other objects by demanding that they conform to a protocol, either by having a variable of that type that they're trying to assign or a parameter to a function. And there's even other mechanisms you're going to see soon when we talk about generics and protocols for demanding that you want that thing to be a movable. It has to be a vehicle, whatever. You can demand it now that you have this protocol. But in all of that, neither side has to reveal what sort of struct or class you are. You completely can be anything you want. You just say you implement movable, and now you can be operated on as a movable. But you could be anything. You could be a car. You could be a portable thing. You could be a boat. Okay, it doesn't. We know when neither side cares. Okay, all one side cares is that you can do the movable things, and all the other side cares is that you implement all those movable things. So this is what functional programming, or really we might call it protocol-oriented programming, is all about. It's about formalizing how data structures in our application function, how they behave. Okay, even when we talk about vars in the context of protocols, we don't define how they're stored or computed. We don't even say whether they're stored or computed. We just talk about whether they're read-only or read-write. And through all this, we focus on the functionality. Okay, we're hiding the implementation details. It's kind of the ultimate promise of encapsulation from object-oriented programming, but it's really taken to a higher level because it doesn't mix it inexorably with the data and all that. It's just talking about the functionality. And all of this gets even more powerful when we combine it with generics. Protocols plus generics equals, as I say here, superpowers. So let's look at how generics, remember that's the don't care stuff that we talked about last time, how it combines with protocols to make superpowers. Here we go. Let's do this by example. Let's say I had a protocol called greatness, and this protocol only has one function in it, which is greater than other. Okay, one argument other to this function is greater than. By the way, this is kind of an interesting function because the type of other is capital S self. That's a special kind of name of a type in a protocol, which means the actual type that's implementing this protocol. Because remember, protocols themselves have no implementation. They get implemented by structs and classes. So that self means the actual structure class that implements this, that is executing it at the time. Okay, so that's kind of cool. And I'm going to show you how that works in just a few clicks here. So if we have this protocol, look at what we can do. Extension array, so I'm adding something to array, where the element, the don't care of the array, conforms to greatness, greatness. So that where I put in red because it's really the key part of connecting generics and protocols. Here I'm actually going to add a var, or I could do it with functions, but I'm going to add a var here to array so that every array where the element, the don't care, conforms to greatness will get this var. Okay, let that sink in. Now this var will not exist in arrays where the don't cares don't implement the protocol greatness. This var just will not be there. If you tried to type it in your code, the compiler would say, oh, this array does not implement greatest. It would only say it implements greatest, only let you type that in without error if it was an array of something that implements the protocol greatness. Now, I like to call this we care a little bit, all right? Normally we call generics don't care, right? Element is a don't care. Array doesn't care what's inside of it. Well, this is kind of, this extension to array cares a little bit about element. It doesn't really care what element is. It can be any structure class, but we do care that it implements greatness. So this is care a little bit. You want to think of it that way. Then this var greatness, look what its type is. Element. It's the don't care. So I'm going to look through the array and find the one that's the greatest by calling is greater than other on all of the things in the array, which I know I can do because this extension to array is only where the elements implement greatness. See how it all works here? So you can easily imagine, I'm not going to show the code here, but you can easily imagine building a for loop that just goes through all the elements, calls is greater than on all of them, figures out which one is the greatest, and that just returns it. Some of you are looking at all this, and I'm sure you're shivering, as I say here. You got to be thinking, holy cow, how am I supposed to be expected to know how to design my code using this technology? I mean, it's just all new to me. And this is indeed a very powerful foundation for designing things, very powerful. But functional programming does require some mastery that only comes with experience. And the good news is that you can do a lot of stuff in SwiftUI, most things, without really mastering functional programming. But here you are at Stanford trying to get a good education. And so the reason I'm explaining this to you now is so that the more you use it in SwiftUI, the more you see it in the documentation where you see these wheres happening, okay, where you see protocols like view and identifiable coming down the road, that you're not just saying, oh, I have to put :view here. You're actually understanding how it's being designed underneath. And the more you see it, the more it's going to sink in, and the more eventually you might start to be capable of doing functional programming design as well. But no one expects you right now to be able to be designing stuff where you're adding extensions to protocols with generics and all that, but eventually you'll be able to. And in the meantime, you'll kind of know what's going on in SwiftUI. All right, so I'm just putting this one slide up here about enum, but once again, I'm not going to talk about enum in this lecture. We'll talk about it soon, not to worry. So that pretty much covers what we're going to talk about today on architecture, and we're almost there in covering this entire topic. And now I'm going to shift gears entirely and go to a completely different topic, which is layout. In other words, how do we decide where all our views go on screen? The way that SwiftUI does this is amazingly simple. It's one of the more elegant things in all of SwiftUI. There's really only 3 steps to doing this. The first one is that container views, like HStacks and VStacks and things like that, they offer space to the views that are inside of them. And then those views choose a size for themselves, what they want to be based on that offer. They could choose a size same as the offer. That's the most common. They could choose a size smaller than the offer. They could choose a size that's larger even than the offer. So they views, in a very kind of good encapsulation way, views decide what size they're going to be. No one tells them what size to be. We just offer them space, they decide. But then after that, the container views, like the stacks, it's their job to position their views inside of themselves. And that's it. These are the 3 steps to get everything laid out in SwiftUI. So let's dive into this a little bit. Let's talk about container views. So the most common container view that you're already familiar with is HStack and VStack. Of course, there's ZStack as well that kind of stacks them on top of each other. But HStack and VStack are interesting in that they divide up the space that's offered to them amongst all of their subviews. And we'll talk about how that works in a moment. For each is kind of a unusual container view. It actually defers the positioning and sizing to the container that it's in. That's why we put our card views that were in that for each into an HStack. So the for each is deferring, letting the HStack decide. And a hidden thing that's going on with layout is modifiers, like dot padding and others. They essentially contain the view that they modify, if you want to think of it that way. And some of them, like padding, do layout. So let's talk a little bit more in detail about HStack and VStack, the most important one, or at least the one that does doing the most layout. The way that the stacks divide up the space that they're offered is they kind of divide it equally, and then they offer it to the least flexible views first. So what do we mean by that? So an example of a very space inflexible view is image. So we haven't talked about image yet, but it's just a view that shows an image, as you might imagine. And of course, it wants to be the size of that image. Pretty inflexible in that way. So generally, the images are going to get the space they want first. Another example of a pretty inflexible view, not quite as inflexible as image, is text. Text always wants to size itself to fit the text inside of it, understandably. But it does have a way to be a little bit smaller and put ... at the end of text, as we'll talk about in a second here. So it's not quite as inflexible as an image. And most views are very flexible. For example, all the shapes like rounded rectangle that we saw, whatever size you offer it, it's pretty much going to take that and it's going to draw itself appropriately in that size. So after one of these views chooses its own size and takes whatever size it wants, that size is removed from the space that the stack is trying to allocate, and then it goes on to the next least flexible views and rinse and repeat until all the space is used up. So it's as simple as that. That's how HStack and VStack apportion their space. Now, after all the views have chosen their size, then the HStack and VStack sizes itself to fit those views with whatever little spacing in between that it provides. HStack and VStack work with any view, of course, but there's a couple of them that I'm going to introduce to you here that really help with layout. One of them is called spacer. So a spacer is just a view that takes all of the space that's offered to it. So if you give it space, it's going to use that space. And so it's used for filling in space. Now, it doesn't actually draw anything. It just kind of uses up space in an HStack or VStack. That's why it's called a spacer. It has that min length argument, which is the minimum size that it should be in the direction we're laying out, horizontally or vertically, depending on whether it's HStack or VStack. Although we usually don't specify, because the default for that is the right amount of space on this platform. One thing that you're going to start to get used to as the quarter goes on, that even though we're focusing on iOS, you can use SwiftUI on Apple Watch and Apple TV, and the spacing and the layout is a little different on these platforms. And SwiftUI is really smart about saying, oh, I'm on an Apple Watch, so I'm going to use this much space in my spacer by default or whatever. So that's why we really want to try and use these defaults and not specify min length when we use spacer. Same thing with spacing on the HStack itself, right? HStack spacing, we don't want to do that. Even padding, generally it's fine to put padding, but if you start putting numbers in there and specifying exact paddings like we saw, you're defeating a little bit of the purpose of this platform independence. Now, sometimes you need it, you just do, but we try to use these defaults as much as possible. So another cool view to put in an HStack or VStack is divider. So divider just draws a dividing line. Again, platform specific. It depends what a divider looks like in the context that it's in. Of course, the divider it's not like a spacer. It doesn't use all its space. It only uses enough space to draw that line. And the line obviously goes opposite to the direction that we're laying out. So if we're in an HStack, the divider is obviously going to be a vertical line. If we're in a VStack, it's going to be a horizontal line. So you're almost certainly going to want to use one or both of these in your next homework assignment, and they're really valuable for doing layout with stacks. These HStacks and VStacks, I told you that they're kind of choosing which of its views to offer space to next, priority-wise, using this least flexible thing, but you can actually override that with this view modifier layout priority. So here's an example of an HStack that has a text that's really important. It's got an image, which we know is very not flexible, and so normally would get a lot of attention from the HStack. And then it has another text, which is less important. So I've added the view modifier .layout priority 100, which I can pick any number I want there. It really doesn't matter. It's a floating point number. And that's more than the default layout priority, which is 0. So when this HStack goes to offer its space, it's going to offer this text space first. And that text is going to say, well, sure, I want to be this big so I can fit this word, important, all the way. Then it's going to say, okay, well, there's no other high priority ones. There could be other ones with different numbers. It starts with the highest priority and goes down. And so now it goes to do the image because that's less flexible than the text. The image gets its space, and then the unimportant text has to fit itself into the space remaining. And as we mentioned before, when a text doesn't get enough space, it will put ... in there, okay, to elide or shorten the text to fit the space it did get. It always wants to be its space. It never wants to be larger than its text fits in. It always wants to be the exact size, but if it's forced to be smaller, it knows how to do ... Another insignificant part of HStack and VStack's layout is their alignment. So imagine you have a VStack, right, a vertical stack of views. And what if those views pick their own size and they're not the same width? Okay, so they can't all be kind of filling the whole width of this vertical stack. So does the VStack left align them or center them or right align them? How does it know where to put them? Well, there's actually an argument to VStack and HStack. We already know that VStack and HStack have the argument spacing, which determines the spacing between the views. It also has another argument, alignment. Okay, and alignment takes an alignment guide as its argument. And one of the alignment guides, for example, is leading. Now, why the leading here instead of left? Or if I want this VStack to have all the views be left aligned, why don't I say .left? And in fact, there's no such thing as .left. And .leading means to have the things in the VStack line up so that their edges start from where text comes from. In different languages, sometimes the text comes from the right and moves to the left, like Hebrew and Arabic. So we want our VStacks to generally match up with that text coming from that side. Text baselines can also be lined up. So HStacks, well, it only makes sense in an HStack. You can line it up so that the bottom of the text, even if they're different fonts, will all be lined up in your HStack. You can even define your own things to line up, alignment guides, and that's a little beyond the scope of this course. So we're just going to use the built-in ones like .center, which is usually the default alignment, is to center the thing in the middle of the VStack or the HStack. But there's also top and bottom, trailing, leading, all these things as you can imagine. And when you start typing it in Xcode, VStack alignment colon, of course, Xcode will help you and tell you what all those built-ins are. That's it for stacks. Okay, stacks very important. But there's this other thing, modifiers like .padding that I said kind of act like essentially container views. Remember that these things, .padding, etc., they return a view. And you might have thought they just returned a view so that we could then send them another, call another function on them, .foreground color, and then that gives us a view back. We call .padding on that, and that gives us a view back and call .font on that. So it's not just to give us a view back so we can call another function on it. Those views that come back might actually be participating in the layout. Now, most of them don't participate, like font and foreground color. They're not affecting layout, so any space they're offered by an HStack or some other container, they're just going to pass it on to whatever view they contain. For the purposes of this slide, we're going to think of a view that these modifiers modify as being contained by that view that the modifier returns, which it kind of is. We're going to see how these view modifiers are made next week probably, or the week after, depending on how things go. And you'll see that kind of really what's happening is that it's containing the view it's modifying. What about these modifiers that actually participate in the layout process, like padding? Let's look at padding. The view that's returned by .padding, this modifier, it offers the view that it's modifying a space that's the same size as was offered to it, but reduced by 10 points in this case, whatever the padding is. It might be, if that 10 is not there, then it would be whatever system appropriate padding. It's essentially removing that 10 because it knows it's supposed to provide the 10. And then the view that's returned by padding chooses its own size to be whatever size the thing that it's modifying ended up being plus 10. So that's what padding does. It adds 10 points around the outside or whatever edges you say of the thing it's modifying. So you see how .padding, it's just modifier, it's just a view that participates in the layout. What's another example of this? You've already used it in your homework. .aspect ratio. The view that's returned by .aspect ratio modifier, it takes the space offered to it and it picks a size for itself that's either smaller than that offered size and has the aspect ratio. That's if we choose the .fit option of aspect ratio. Or it could be bigger than the size that's offered to it. That's the .fill option that uses all the offered space. And so, yes, it is possible when you're a view and you're offered a certain amount of space, you can choose your size to be larger. Now, that's rare. We don't generally want views kind of spilling out all over each other, but it makes sense. Like in this aspect ratio fill, maybe that makes sense. So then the aspect ratio view that's now sized itself to have that aspect ratio offers the space that it chose to whatever view it's modifying, like our card view. So our card view fits itself then in that nice aspect ratio space. So let's see an example of a full layout happening and the size being passed around and things like that. So here's an HStack similar to the one we have in our Memorize game. Not exactly the same, but very, very similar. How is the space for this thing apportioned? Well, the first thing to understand is that the first view that's going to be offered, the space into which this whole green thing goes, is that padding view. It's the outermost view. It's actually the view that is this whole thing in the end. It's going to be offered whatever space is available for this whole green construct here. Now, what it's going to do, it's going to take 10 points off the edges of it and pass that space that's left onto the next view, which is the view returned by the foreground color modifier. Now that modifier isn't really participating in the layout, doesn't really have any effect on the size and position of the thing, so it just passes that on untouched to the HStack. Now the HStack, as we know, is big time layout view. It's going to divide up its space starting out equally. And since the aspect ratios aren't things like images or text that are fixed sizes, it's going to end up dividing that space equally among all of the aspect ratio views in the for each, because we know the for each itself just defers to the HStack. So it's the aspect ratio views now that are being laid out in the HStack. Each aspect ratio view is going to set its width to be its share of the HStack's width, and then pick a height that matches the aspect ratio, the 2/3 aspect ratio. Or if the height is limited here, it might be the other way around, where the aspect ratio view takes all of the height it's offered and instead chooses a width that's less to fit. So it could go either way. It depends on whichever is going to fit best in the space that is offered. Then the aspect ratio has picked that size. It's going to offer that to the card view, and the card view is going to use all of the space because it's like a normal view. Whatever space you offer it, pretty much it's going to use. After all this offering and sizing happens, what's going to be the size of this whole green view? Well, it's going to be the size of whatever view.padding10 returns, which is the result of the HStack sizing itself to fit all those aspect ratio views, plus 10 points on all sides. That's going to be the size of this whole green thing. Let's talk about views that take all the space that's offered to them. Obviously, things like rounded rectangle, it's real easy for them. They just draw the rounded rectangle all the way to the edges of what they're offered. But what about custom views like card view? Card view we built out of a ZStack with rounded rectangles, text. We're building this thing. It takes all the space that's offered to it, and there's no reason it shouldn't, but it should really be adapting itself to whatever space was offered. And we really see this desperately with the font size of the emoji. And in your homework, I asked you for really small cards to switch to a smaller font. And I'm sure you probably realize, wow, this is a really bad solution to this problem. And of course it is. Really what we need to do, and we're going to do in our demo, is pick a font size that is, related to the size that we're offered. Since we're going to accept the size offered to us, we should pick a font size that fits it. So how does a view know what space was offered to it and can make that font choosing decision, for example? Well, we do that with a special view. It's just a view, but it is kind of special, called GeometryReader. And what you do with a GeometryReader view is it wraps around whatever thing that you want to adapt to the size. And so this would normally just take whatever's in your body and you just wrap GeometryReader around it like this. GeometryReader is just a view, and I'm not showing you the obvious thing here. GeometryReader, open parentheses, content, colon, all this, just like an HStack or whatever. This is just the content. But you do notice that it has a little argument there, geometry in, similar to how for each has an argument, which is the thing we're iterating over. This also has an argument. So this argument is of type geometry proxy. And this geometry proxy is just a struct. It has some nice information in there, the most important of which is the first one you see, var size. That is the size you're being offered. The width and height, CG size is a width and height that you're being offered. And you can use that size. It's in points, and of course font sizes are in points, so it's going to be pretty easy for us to pick a font size that fits nicely in that size. You see some other things here, like the frame is actually not only the size, but it's a rectangle where we are in a certain coordinate space, like our parents' coordinate space or the global coordinate space we can even look at if we like. And I'm going to talk about the last one there, safe area insets, on the next slide. One thing to remember about GeometryReader, it's just a view, but it always accepts the space offered to it. And I underline that because it requires a little sinking in, because you don't want to get into a recursive loop here where the GeometryReader is reading its size and then you're trying to actually change the size of the GeometryReader based on the size that it read. It doesn't work that way. GeometryReaders always accept the size, the space that's offered to them, and you have to think of it that way. So GeometryReader's utility is just limited to knowing what size you're being offered and adjusting how you look on the inside. That's what GeometryReader is for. Don't try to twist GeometryReader into something it's not. It's just reading your geometry. It's called GeometryReader. It reads the geometry and you adapt to it. So you can like change your font or things like that. All right, the safe area thing that we mentioned, that safe area incest that the GeometryReader tells you about. The safe area is best visualized by thinking of the notch on the iPhone 10. Most of the time, you don't want to be drawing up on the sides where the notch is up there. Not always, though. Sometimes you might actually want to draw up there. And there's other safe area things too. Sometimes views will add adornments or the way they kind of draw on screen where they don't want you drawing in certain spaces. So they kind of create this safe area for you to draw in. But if you want to go outside your safe area, you can. And the way you do that is by the view modifier here, edges ignoring safe area, and you specify which edges that you want to ignore that safe area. So if I say edges ignore a safe area top, then that ZStack and everything in it is going to ignore that there's a safe area on the top and just draw right up on underneath that notch up there. And so like if you're a photo viewing app or something, maybe you want to go all the way to the edges. So you can do that here. All right, let's talk a little bit about how containers do what they do, which is offer space to their views and then position them. It offers space with this modifier frame. Now, I'm not going to talk about frame in detail here. You can go look at the documentation. Frame has quite a lot of arguments, ideal width, minimum width, all these kinds of things to try and communicate to the views. Here is where the space that I'm offering you. All right, so that's how it offers space. And then once the view has chosen its own size, then we're going to use this modifier, position, to put it somewhere in our coordinate space if we're the container. So that's how they do that. Pretty straightforward. Stacks, for example, would use their alignment information and the spacing and all that to figure out where their views should go, and it would set this CG point, which is the center of the view, set the CG point for each of the views. By the way, there's kind of a cool little modifier here called offset, which will offset the view from wherever a container put it. So you can let the container do its job, put the thing somewhere, and then you can still offset it a little bit by something. And the container could do this, but also someone else could do it. The view could do it to itself. I want to be offset by a little bit. So offset is kind of a fun little one. We don't use offset that much, but I just want to let you know it's there. Now for memorize, we're going to use frame and position to create our own container view, which is kind of like a stack. It's going to be called a grid, and it's 2D, rows and columns, right? Instead of just a horizontal row, which is a pretty sad looking game, if I do say so myself right now. And we obviously want that to be rows and columns. We'll do that by using frame and position to create our own container. So we're going to go back to the demo today. I'd love to have time to actually go do that container, but we don't have that. It's the end of lecture 3 here. I do have a short demo, though, I'm going to do just to show you how GeometryReader works. And what we're going to do is what I've been talking about, make our font, our emoji font, size better to the space we're offered using a GeometryReader. While I'm there, I'm going to do a quick little thing where I'm going to show you the best way, or the kind of way we've all agreed on, to collect magic numbers in our code, which we already have one in there, like corner radius 10. That 10 is a magic number. It really shouldn't be embedded in our code. There's kind of a canonical way in Swift to take that out and put it in its own little space so it's well documented and typed. All right, now we'll start our next lecture though using GeometryReader and also generics with protocols and functions as types to make this beautiful little simple grid view that's just going to be like an HStack. We're going to replace our HStack by just using this grid view and make our cards be in a nice grid. So let's hop into that demo, and then that'll be the end of this lecture. Now in your homework, you were asked to adjust the font choice here to fit really small cards, because small cards, the font we chose, large title, was too big. And that might have fixed it just for small cards, but I made you do that almost to realize, well, that's no good solution, especially when we're in landscape where even large title is way too small. So what we really want is for our card to pick a font that uses all the space. That's really what we want to do. So how are we going to do that? Well, we're going to do that with a special view. It's another view, just like HStack is a view, and for each is a view, and ZStack is a view, text is a view. These are all just views. There's a special view that is called the GeometryReader view. So GeometryReader has one argument, which is the content that it's going to display inside of itself, which is just another view, like our card. Okay, that's the stack that we make our card. But it has a nice argument here called geometry. Just like for each was a view that had an argument here, but it also had this content argument, and it provided the card that it was iterating through. Same thing here, GeometryReader, it has content, asks for a view, but it provides this special geometry. And we're going to look at this little variable that is given to you inside here, because we can look at this and see what the size of our view is. Now notice that when we put our code, our ZStack, inside of a GeometryReader content, we got these requires self dot things. So to go through here and do a fix, go to this one, fix that one as well, pick that up. All right, so what is this? Let's take a look at the documentation for GeometryReader. So I'm going to do Option click to look at GeometryReader, and you can see here struct GeometryReader. It's got a don't care called content, where that content is a view. And so now hopefully you are starting to understand what that means, where content is a view, right? Content is a don't care, view is a protocol. So we've turned that don't care into a, well, we care a little bit, right? We care that the content of a GeometryReader is a view, but otherwise it can be anything at once. And so I'm going to open that in the documentation and take a look, see what it says. And here's the init. You can see that it takes this one argument content, which actually you should be recognizing this syntax here, because really it takes a function that returns this content don't care, which we know is actually a we care a little bit, content where content colon view, so we know it has to be a view. And so that's a function, right? Function that takes an argument geometry proxy and returns this don't care content. Don't worry about that @ sign escaping there. We'll be talking about that in the weeks to come. So let's click on this geometry proxy and see its declaration. Here it is, and you can see it has the things we talked about in the slides. Now I'm going to focus obviously on the size right here, so let's click on that. And you can see that size is just a CG size. It's get only, it's read only. It's just going to tell us the width and height that we've been offered to draw this view in. All right, so that's exactly what we want. We want this geometry size right here. And what I'm going to do is I'm going to have my card view take ownership for setting its own font right here. So it's going to go to font. So I'm no longer setting the font in the game itself. I'm letting the card set its own font, which is probably better encapsulation anyway. While we're here, of course, we don't need this colon content thing, just like HStack and all these other things. We can get rid of that and get rid of that. So this looks a lot cleaner there. So we want to do a font here, create some font whose size is based on that geometry size. So I'm going to create a system font. There's different ways to make a system font right here, styles and sizes. So I'm just going to pick size. It wants a CG float with the size, the point size. And remember, the point size of a font is related to the point width and the point height there. So I'm actually going to pick the minimum of the width of the height, because I don't necessarily want to depend on knowing what my aspect ratio here is. And so I'm just going to pick the minimum of those two to make sure that I pick a font that fits. So that's min of geometry's size width and the geometry's size height. Right, so I'm using that size var that we saw that's in this geometry proxy right here. And maybe we could just try this. Let's just pick a font size that is the minimum of these two and just see what this looks like. So let's run this. And look at that. So that is a much closer size. Oh, and you even got smaller. But this is actually a little too big. See, it's got a little too big there. Maybe that's just because font point sizes aren't exactly the width of the font. It may probably closer related to the height, but also we do put a little stroke around the edge. That takes away a little space as well. So probably I need some sort of constant multiplier here, like maybe times 75%, 0.75, something like that. Okay, and 75% actually looks pretty good. Okay, looks good when it's big, looks good when it's small. Before we finish up lecture 3, I want to take just a moment here to talk about a coding style issue. I don't often talk too much about coding style purely for time constraints in these lectures, but this time I am going to mention this because it's a little bit of a segue into how we're going to structure our view code to make it as readable as possible. This problem I'm worried about is these magic numbers. We've created these blue magic numbers and started to sprinkle them out throughout our code. That's not very good coding style. SwiftUI is declarative. We're essentially declaring the UI directly here. We're not calling functions to tell it to build itself. We are declaring it right here. And when we do that, these blue numbers end up being kind of the knobs that we can turn to fine tune the way our view looks and get it just right. Well, right now our knobs are just spread all over the place here. Really nice if we could have a control panel. So I'm going to create a little control panel. I'm going to comment here to mark it, drawing constants, I'm going to call it, and put all my drawing constants down here as just vars and lets and functions on my struct. And this idea of putting vars and lets and functions in your struct to clean up or fix magic numbers in your view, really important. You're going to see that most views have a few vars and lets and funcs down here to make this look as clean and understandable as possible. So let's use this idea to get these magic numbers out of here. These happen to be constants. So I'm going to use let. Remember, let is like var, except for let means it's a constant. So let's do the corner radius up there, corner radius. You might think you could say corner radius equals 10, but this doesn't work, and I'm going to show you why here. If you hold down the Option key, remember, and click, it'll tell you the declaration of this thing that you clicked on. In our case, it's our corner radius, and it has been typed as an int. Remember that if we say let a var equal something and we don't specify its type, Swift will infer it. And here it's looking at this 10 and inferring, looks like an int. That's not what we want. All of these blue numbers in here are CG floats, floating point numbers we use to draw. Now, I can't even just say 10.0. If I do that and Option click, it thinks it's a double. These are not double precision floating point numbers. This double struct is not the same as a CG float struct. So I have to explicitly type this, CG float. And that's not necessarily that burdensome or onerous. It's kind of nice in a way to remind myself these are drawing constants down here. Let's do our other ones. We got the edge line width is another constant we have up there, that number 3. And of course we have this 0.75, which is really like a scaling factor for our font. So I'm going to call it font scale factor. That's also a CG float, 0.75. Now that I have these down here, I can replace all my magic numbers with these, and this becomes the knobs on my control panel. So let's do that. We got this one, that. I'm going to copy and paste, make this go a little quicker. And over here, this 3 is this edge line width right here. And our font scale factor here is this 0.75 here. This is nice. This actually makes this code read nicely as well, pretty much like the English language, trying to understand what's going on. However, you notice it's introduced a whole slew of errors here. They're actually all the same error. It's the dreaded explicit self dot to make capture semantics explicit. And we could just fix this one and click here and fix this one and I click and fix it. But I'm going to show you a trick for avoiding this self dot thing in this common case of GeometryReader. So whenever you do a GeometryReader, the stuff inside is always going to complain about this self dot. By the way, same thing with for each. For each, stuff inside is going to complain about self dot. Not every view does that, but those two do, and they're commonly used. I'm going to create a func, which I'm going to call body for size, CG size. And it's going to return my body, so that's going to be some view. Just like I can have some view be the type of this var, I can have some view be the return type of this func. And I'm going to put my body, to cut it out of here, and put it in here. And then just call this function in my geometry reader, self.body for the geometry's size. This code cleaned up actually kind of nicely. Makes perfect sense. And this code now is no longer embedded inside this geometry reader like this, so you don't need these self dots. So I can get rid of that one and that one and that one and this one. All those self dots are gone. What's more here, I didn't pass the entire geometry to this body, just the size, the geometry size var. So down here, I don't need to say geometry.size. This geometry.size is now just size, this size that I passed in. So that makes this code look a lot nicer, and I almost always recommend, at least for the next couple months until they put that Swift self dot change in there so that self dot is not causing this problem anymore. This is a real clean way to have this code not have to worry about self dot. And you can do the same thing, body for item in a for each, because for each is going to cause that self dot problem as well. We could do one other thing. Here I could have a func for the font size called font size for size. Have it return a font size, which is also a CG float, and put this code right here down in here so that this just reads font size for size. You might think this is a very simple expression. I don't really need to turn it into its own func here. But again, you can't make this too simple. You really want to have this be as simple as possible. And sometimes you're forced to make it simple. These ifs, as I explained, can't be arbitrarily complex expressions. So sometimes this needs to be a function that returns a bool, not in this case, because this is simple bool. But making these little one-liner functions that make this body look cleaner, very common. Here we might even not have to have this font scales factor be its own separate let, because you can kind of think of the font size as just part of the drawing constants. This is the constant font size for a given size. So that's it for lecture 3, and we're going to dive right back in at the start of lecture 4 and continue with this demo and make our HStack up here be a 2D grid. We're going to learn a lot of stuff doing that.
For more, please visit us at stanford.edu.